Okay, the next talk is titled Compact Key Storage in the Standard Model. This is joint work with Evgeny Dodis and Daniel Yost, and the speaker is Daniel.
Okay, thank you for the introduction. So this is a follow-up work on our paper at Last Crypto, where we introduced compact key storage as a primitive. And given that I don't assume that you've all been there, let me briefly spend some time recapping the notion. So the setting is essentially secure messaging, where it turns out that people don't just want security to transmit their message, but they apparently also really hate to losing their data. As a result, essentially all the practical applications employ some sort of backup mechanism so that users don't lose their data. Unfortunately, it turns out that many of the existing backup mechanisms are quite naive. For instance, what WhatsApp does is they just pick one static key, they encrypt the whole backup under that one static key, and as a result, you don't get the same type of nice security guarantee that we actually have on the communication layer. So in our work, we try to do better, and the first observation we made is that actually, if you look at secure messaging protocol, what most of them seem to do is that they have some sequence of keys that they use to symmetrically encrypt the messages. So we had the idea like, okay, can we not just back up the original ciphertext as one step, and then as a second step, back up those keys? And CKS, in a nutshell, is essentially a clever mechanism of backing up those keys. A bit more detailed, what we want is that this backup is shared amongst all the users of a group. So if you have a group chat with hundreds of people, then the server storage should not scale in the number of people, but they should all be able to use the same server storage. Secondly, each user should of course be able to retrieve the keys they once knew, and for security they should only be able to retrieve those keys and no more. And finally, we also consider some advanced functionality, such as delegation of keys, like if a new member joins the group, maybe you want to grant access to parts of the communication history, or maybe some people want to selectively erase some old message, and therefore it would be nice if we can actually support this. So I will not formally introduce the CKS syntax because it's a bit cumbersome, and instead just do some basic introduction by example. Let's say we have a group chat with two parties, and initially they have one key. So in the CKS scheme, they both take this key and they use it to initialize some kind of local state, and then one party uploads something to the server who also initializes a state. And importantly, for efficiency, we want that only one party needs to upload something to the server, and the other party should be later able to just use the local state and the server state to retrieve their key. So if now another member joins and the group key and the key gets rotated, then the two existing members update their local state, the new members initializes a new state, and one of the member again uploads something to the server. This could be the same party, this could be another party, it shouldn't matter. And importantly, now the local state of the existing member should be able to recover both keys, while the local state of the new member only should be able to recover the new key. So if a third key shows up, the same happens again. And yeah, eventually the local state should grow up linearly in the number of keys. That's why we call it compact in compact key storage, while the server state, of course, will grow linear, if not even polynomial, in the number of keys. And we can also support removing parties. We can support local erasure, like Tweety can say, I no longer want to store key 3, and so on. I hope you get the gist. So what about security? Intuitively, we would want that CKS does not hurt the security of the key. So what does that mean? Well, it should mean that the keys look indistinguishable from a random key, even when giving the server state. Unfortunately, it's quite easy to see that this is impossible to achieve. Therefore, in our work at Crypto, we introduced a slightly weaker security notion, which we called preservation security. And in a nutshell, preservation security says that adding CKS to an existing application, such as a chat, should not hurt the security of the chat. And as a first contribution of this work, we show that when in the standard model, even this weaker security notion is impossible. So how does preservation security look? First, we define the notion of a CKS-compatible application. Roughly speaking, we just require that there is a sequence of keys to which we can actually apply CKS. Then, additionally, we also require that the application can tolerate a testing oracle where an attacker can submit a guess for a key and be told whether this is the correct key or not. I will not go into the detail too much why this is necessary, but I just want to say that most applications are fine with that requirement, and only few, like the one-time pad, really break. Preservation security then says that the CKS scheme is secure if, for any CKS-compatible application, the security is preserved when adding CKS. So why does that break in the standard model? Essentially, this class of CKS-compatible application is intentionally broad so that we capture as many applications as possible. Unfortunately, it then also contains contrived applications that essentially contain a trigger condition that test whether you're executing CKS, and if so, just leak all the secrets. How did we circumvent that in the crypto paper? Well, there we assumed that the CKS scheme can make use of a fresh random oracle that's not available to the application. So let's briefly go through the impossibility. Let's say we have a CKS compatible game and let's assume we have fixed the CKS scheme. Then this game just samples some keys and it runs internally CKS for one user, producing both a local and a server state. The local state is then sent to the attacker, and for this to be a CKS compatible, we'll allow this testing oracle. But eventually the attacker just sends like guesses for all the keys and wins if and only if all of them are correct. Now, given that we require the local state that we send to the attacker to be compact, it's quite easy to see that by entropy, the keys overall still have a lot of remaining entropy, so this will any attacker will only win with negligible probability. What happens, however, now if we add CKS? So we essentially also execute CKS on those keys. So actually, we now have two users running CKS, the one that actually runs it and the game that internally runs it. And then we give the server state to the attacker. However, by correctness, because we want that only one party needs to upload stuff, with the state that the attacker is given, he can now recover by correctness all the keys and therefore trivially win this game. So this is a game that's not secure for any for this specific CKS application. Okay, what can we do instead? Well, we said, okay, can we keep the original security definition, but instead consider weaker functionality? And this is what we do in this work. Roughly speaking, we had a key derivation step. So before parties had like keys that they backed up, now we say they initially learn some seeds that they back up, and when they do the recovery, they only get some derived keys from those seeds. And we observed that for most applications this still seems fine, either because we can design the application with CKS in mind to begin with, or because many of the applications actually do some kind of key derivation anyway. Okay. And once we do that, we can stick to the original very simple pseudo-random key definition. So let me briefly mention how we can now construct such a scheme in the standard model, and it's actually quite simple. The main ingredient we use is what we call a trapdoor key derivation function. First and foremost, this is a key derivation function, so it takes a seed and produces a key. But then there's also this whole trapdoor process. So there's the derive function, which takes a state and a seed and produces an updated state and a ciphertext. From this updated state, we can then derive a trapdoor, and from the trapdoor and the ciphertext, we can recover the key as well as the previous state. So we have seeds and key. We input seed, get out key, and we input state and get trapdoor. And sort of this additional derivation step is really what avoids the impossibility in the standard model. So how do we construct such a trapdoor KDF? Well, we can construct it from very basic cryptographic primitives. So we take the seed, we just apply a PRG and get the key as well as some intermediate value X. Analogously, we take the old state, expand it, get the trapdoor as well as another intermediate value Y. The two intermediate values we then combine using PRF into the new state. And finally, we take the current trapdoor as an encryption key to encrypt the previous trapdoor as well as the key. And just for completeness, this needs to be deterministic, but that's fine here. Once we have a trapdoor KDF, we can quite trivially build a CKS scheme by just iterating it. So at any point in state, we can derive the trapdoor from a current state and reverse the whole process. This works if we find that all the parties need to know all the keys. We can also do something more clever, like a tree. And actually, in the paper, we show that you can combine it according to any directed acyclic graph, and it's secure. And the actual choice of directed acyclic graph gives you some efficiency functionality trade-off. Okay, that's essentially it.
Any questions?